Okay, so we're supposed to consider a right triangle. So I'm going to stop, draw a right triangle. I'm done with that. With a side length x that's opposite angle A. So we'll just call this angle A. And that means this is x over here, okay? Because that's opposite of angle A. Side length y that's opposite angle B. So I'll put angle B up here, and I'll put side length y over here because that's opposite. And then a hypotenuse of length z. So that's why I didn't label this A. I didn't label this B because I had already read ahead a little bit in the question that the hypotenuse is supposed to be z, and the hypotenuse is the side that's opposite of the right angle. Oh, I forgot this. This is 1/2, I think, for this problem. They tell us that sine of B is 1/2. Sine is talking about a ratio of two sides in the triangle. So like sine of some angle theta in a triangle is the side that's opposite of the angle. I'm just going to abbreviate. Divide by the hypotenuse of the triangle. That's all a sine function is. Sine of some angle is the opposite side divided by the hypotenuse side. So I think this one works out so that it has special angles, but I think I should do this in a more broad way because some students' questions won't have like the 30-60 triangles that we see in our text and in some of the other videos. Let's work with this idea over here. Sine of B is 1/2. What we're going to do is we're going to draw a similar triangle. Okay, which means it's like another triangle, just it has different side lengths. The ratios are still the same. Like if you take this side divided by this side, it will equal this side divided by this side if it's a similar triangle. And let's keep this B, let's keep this A. And what the sine function does for us, sine says the opposite of B is 1 because sine is the opposite divided by the hypotenuse. So opposite of B is 1. And the hypotenuse of the triangle is 2. Okay. The reason why I had to draw a smaller, similar triangle is because all we have is the ratio. We don't have what the actual scaled values are for each of these. Okay, actually they tell us that x is 17, but we don't have what this value is, what this value is. All we have is what the ratio is after you divide them and simplify the fraction. So I got to draw this smaller triangle, and then I can use this smaller triangle and use this side length to scale up to the bigger triangle. Okay. So there's like a number that you can multiply this side length to make it equal this side. You can multiply 2 by something to make it equal z. You can multiply 1 by something to make it equal y. That's what a similar triangle tells us. Okay, it's just off by some multiple. And so to figure out what the multiple is, we can use this information. We know in the big triangle, x is 17. We can find out what it is in the little triangle and then just figure out what it takes to scale it up. Okay, so to do that, we just need the Pythagorean theorem, right? This is the hypotenuse. So we got 1 squared plus, let's call this j, just some other letter. 1 squared plus j squared equals the hypotenuse. It's important that this goes in for the hypotenuse, right? And now if you solve this, you're going to get j squared equals 3, or in other words, j equals the square root of 3. Right? Subtract 1 from both sides. 4 subtracted by 1 makes 3, and then take the square root. So this is the square root of 3. So now we can find out what that scalar is. We'll call the scalar another letter. Let's just use a Greek letter alpha because that's usually used for a scalar. What happens with the similar triangle is you can take the small side, multiply it by some scalar that we don't know, and that should equal the larger corresponding side. So square root of 3 times something makes 17. And that's a quick little equation, right? Think of that as just like an x. If you divide square root of 3 from both sides, now we know what the scaling factor is from our similar triangle to our larger triangle. Okay, we just have to multiply by 17 over square root of 3 to make that happen. So to figure out what y is, I need to take the smaller triangle's length and multiply it by our scalar. So y is nice and easy. 17 over square root of 3 times 1 makes 17 over square root of 3. That's what this is here. Okay, or it depends. I think Mobius is pretty accepting. This is also the same answer because you can multiply the top and the bottom of the fraction by square root of 3 to rationalize the denominator. And if you need help typing either one of those in, I would type y equals parentheses divided by parentheses. That way I have a numerator. Okay, so that's what I'm typing in is this answer over here. Y equals 17 times square root of 3 divided by 3. That's one way of typing in this answer. Or Mobius, it should be okay with this too. Y equals, there's my numerator, there's my denominator. Our first answer here was 17 divided by square root of 3. That's how I type that one in. Okay, and then to get from this to this, we just have to multiply by that scaling factor that we found for alpha by 17 over square root of 3. So 2 times 17 over square root of 3, that's going to equal z. That's going to be the bigger something. So this is just multiplying the numerator by 2. So that's 34 over square root of 3. But again, rationalizing the denominator, you can multiply the top and the bottom by square root of 3. So you get 34 square roots of 3 over 3. That's the same answer. Either one should be okay. So if I type that in Mobius, parentheses for the top, parentheses for the bottom, the first answer I had written here, kind of going out of order with what I did with the y's. But that's 34 over the square root of 3. And then if you wanted to type the second answer, that's numerator, denominator, that's 34 times square root of 3 divided by 3. Kind of got cut off, but that's a 3 right there. Okay, so that should be everything for this problem.